Yep.
Or n plus n.
I mean, you've got it. Yeah, you've got it right there. Okay?
Are we going to have to do all three parts of this trichotomy?
You are going to have to do one part. I'm only going to do one more part. Okay, so m plus n bigger than 0. But you don't have to necessarily, again, you need to be lazy and think about whether or not you can use what we do to do the last part, okay? So, you know, the goal here should be to think carefully about this, right? Okay. So here's a little bit of trickery. Then m is equal to m plus n plus minus n. Why is this helpful?
Because
Where is that?
it's in the naturals. For which
Where is that?
it's in the naturals. So it's a natural number plus a natural number.
Yep. Why is this useful? Well, let's try it. A-M, A-N. And now I'm going to write out m that way. A to the m plus n plus minus n. A to the n. Yep. So then these are both natural numbers. So this is the n case, right? Natural number plus natural number, I know what that is. That's a to the m plus n, a to the minus n, a to the n. And then what? Well, we already checked that this is okay. So this is a to the m plus n. You'll see this little trick all the time, right? It just happens. You've already seen it many times in here. It happens when you prove the product rule for derivatives, okay? I mean, it's just a standard kind of trick, all right? And then the case m plus n less than 0 is an exercise.
Kind of cheap, honestly.
What?
It's kind of cheap, honestly.
Cheap,
This number,
clever.
number plus and minus any other number.
Yeah. But see, the hard part is figuring out exactly when to use it, right? Because the reason why things like this are tricky is because, first of all, you have to figure out to do it. And then you have to figure out what is it you're adding and subtracting, right? So it's easy only in retrospect.
Just a quick
Yes.
question. What's the little scribble you wrote above A?
Uh-oh.
The end?
Scribble, scribble, scribble. Oh, here?
Yeah.
Okay, this is the previous case.
Oh, like that's what the equal sign.
For n. I said n case, but this is the previous. Right, that's why we split it up this way, because these are both natural numbers. And so I've already proved that, and again, this is where you have to think abstractly, right? I already proved that a to some natural number plus another natural number is a to the first natural number times a to the second natural number. And mainly I had to check that these guys were both natural numbers. Okay? Fun. So, you get to do the last one as an exercise. Again, be lazy. Okay? And think about what's already been proved. Questions about this? Okay, well, we are pretty much done with that section. You have a couple interesting exercises about density of the rational numbers, which is actually quite important. And so now we're going to fast forward to start on binomial theorem. And at this point, we don't have time to go through the whole theorem, of course, but I'm going to start by reminding you of the choose function. Okay, maybe you've heard of this. N choose k. That's how you read it. You read it n choose k. And I'll say why in a second. The definition of this thing is n factorial divided by k factorial, right, times n minus k factorial. Okay, and if you remember, okay, so now n factorial we can actually define iteratively, so why not? So n factorial is defined iteratively. Actually, we have a special base case here, right? 0 factorial, that's actually defined to be 1. That's not our base case, actually. This is a special case, right? And the base case is 1 factorial, which also equals 1. And there's a reason why we do this. You'll see why we do this shortly, okay? Why we make 0 factorial equal to 1. And then what is n plus 1? This is another iterative definition. Factorial is equal to what?
N plus 1 times n factorial.
Yeah. Okay, so for example, 2 factorial is 1 times 2. 3 factorial is 1 times 2 times 3. 4 factorial is 1 times 2 times 3 times 4, etc. Okay, but you see this, it's nice sometimes to write down examples, especially when you have a new iterative definition and you're trying to figure out what it, get a sense for it, get a feel for it. Then it helps to write some things down, right? And of course, now this is just a number, 2, and this is 6, and this is 24, and so on. Okay, if you got to the point in calculus where you were doing power series, then of course factorials come up all the time there, right? And they come up in lots of situations. Okay, so the choose function then is defined using factorials. And this is the number of ways to choose k socks from a box of n socks, or sheep, or planets, or whatever you want. Okay, it's the number of ways to choose k things from a box of n things. So let's just think about this a little bit. Let's look at a couple special cases I'd like to look at. How many ways can you choose 0 socks from n socks?
There's only one way to take.
Yeah, you just don't choose any. Right? Well, so let's check, right? I mean, it's the only way to do it. You just don't choose any. Okay, so this is going to be n factorial divided by k factorial, which is 0 factorial, right? Times n minus 0 factorial. And now you see why we define 0 factorial equal to 1, because it works, okay? There are much deeper reasons for that, but at this stage, yeah, it works in this formula, okay? So that's just n factorial over 1 times n factorial equals 1. Okay, so there's one way to choose. Okay, now, next thing we want to check is choose n. So how many ways can one choose n socks out of a box of n socks? Exactly 1. You just pick them all, okay? And I want you to notice something, right? So I want you to notice that these two things are completely symmetric, right? You have the same thing in the numerator and you have basically the same thing in the denominator. And that's true because these two things are symmetric, right? As k counts upward from 0 to n, n minus k counts downward. Okay, so you see some reflective action going on there. All right, we won't talk about socks anymore, but I want to do a basic formula that shows you how to get something called Pascal's triangle, which you may or may not have seen. So we want to, let's just call this a lemma. We want to show, and this should tell you something about iteration, right? We're interested in how to get n plus 1 choose k from the n choose function. And that's how you do it. Okay, so let's try adding the two fractions on the left. N choose k plus n choose k minus 1. What is that? That's n factorial divided by k factorial times n minus k factorial, right? That's just the definition. Plus n factorial divided by, and now here we have k minus 1 factorial times n minus k minus 1 factorial. Now we're trying to add two fractions. So if I'm going to add two fractions, I want to have a common denominator. So how am I going to add a common denominator between these two? Well, what's missing between these two and on which side? Yeah, to get k factorial here, I have to multiply k minus 1 factorial by k. And then I have to do the same thing in the numerator. Right? Now, what is another way to write n minus k plus 1?
It would be n minus k plus 1.
K plus 1. Okay, and so what now is missing over here?
N minus k plus 1.
Yeah, I need to multiply this side by n minus k plus 1. Because remember, this is a factorial, right? This marches all the way up to n minus k. Multiplying everything together. This one marches all the way up to n minus k plus 1. So there's one missing factor between this factorial and that factorial, and it's missing on this side. And I have to do this in the numerator and the denominator, right? So everybody agree that I now have a common denominator? I multiplied each side by 1. Yes? Yes.
The k minus 1 factorial on the right fraction.
Yes.
How does that?
If I multiply that by k, what do I get, according to my iterative definition?
K factorial.
Exactly. And same thing over here, right? If I multiply, what do I need to multiply this by to get that? This has one more term in the factorial, right? It has n minus k plus 1, because that's the next thing after n minus k. So I have to multiply this side by those two numbers. Okay? All right, let's collect some stuff then. Okay, now rather than really messing this whole thing up here, right? Just see that you got an n factorial and, right, factor that out. Common denominator. So what do you get here? You get you get n minus k plus 1 plus k times n factorial. And then down here, I get k factorial n minus k plus 1 factorial. So it's starting to look like what we need, right?
K and negative k on the bottom.
Yeah, these guys cancel, and I get n plus 1 times n factorial over,
And then you can rewrite that as n plus 1 minus k.
yeah, that's n plus 1 minus k. So that's the second time we've rewritten that little guy, right? Okay, so this is now n plus 1 minus k factorial, right? So this is now k factorial times n plus 1 minus k factorial. And now what's the numerator?
N plus 1
It's just n plus 1 factorial divided by k factorial, and I'll rewrite this, times n plus 1 parentheses minus k factorial.
Which by definition is n plus 1 choose k.
Yeah, that's exactly. Okay, so your homework is due on Friday, but your other homework is going to be to go through this argument and become very, very, very familiar with how factorials work. Because on Friday, and we are having class on Friday, break starts Monday actually, right? That's the official break. So I expect you guys to work hard on your homework both weekends over break, but anyway. Make sure you are familiar with how these things work, because we're going to prove the binomial theorem next time, and if you're not comfortable with it, you might get lost. Okay, so we'll see you next time or at office hours.